In this session, we are going to discuss about electronic configuration, Aufbau Principle, Hund's rule of maximum multiplicity, and Paulis Exclusion Principle. In the last class, we studied that the shells are further divided into subshells and the orbitals are present inside the subshells. Here we can see that the first shell, that is n is equal to 1, has got only one subshell and it is named as 1s. Similarly, second shell has got two subshells and they are named as 2s and 2p. Third shell has got three subshells, 3s, 3p and 3d. The fourth shell has got four subshells and they are named as 4s, 4p, 4d and 4f. The orbital distribution in each subshell is given here. We already learned that the s subshell has got only one orbital, p3, d5, and f subshell has got 7 orbitals. Each orbital can accommodate a maximum of 2 electrons. So s can accommodate 2, p6, d10, and f can accommodate 14 electrons. The electrons first enter the 1s orbital, followed by 2s, 2p, 3s, 3p, 3d, etc. Now we will write the electronic configuration of hydrogen atom. Hydrogen has got only one electron, so it will enter the first shell. The first shell is then divided into one subshell and one orbital. So the electronic configuration of hydrogen atom is 1s1. The electronic configuration 1s1 represent the address of the electron. This means that the electron is present in the s subshell of the first shell. Thus the quantum number helps to determine the position of each electron. Next we will write the electronic configuration of helium atom. The atomic number of helium is 2, which means that helium has got 2 electrons. So the electronic configuration will be 1s2. This means that 2 electrons are present in the s subshell of the first shell. The electronic configuration of other elements are given here. Lithium has got 3 electrons. The first 2 electrons will enter the 1s orbital. The third electron cannot be accommodated there, so it will be promoted to the 2s orbital. So the electronic configuration is 1s2, 2s1. Similarly, the electronic configuration of beryllium is 1s2, 2s2. Boron has got 5 electrons. The first 4 electrons will enter the 1s and 2s orbitals, and the third electron will enter the 2p orbital. So the electronic configuration is 1s2, 2s2 and 2p1. Similarly for carbon, the electronic configuration is 1s2, 2s2, 2p2. The filling of electrons in the atomic orbitals is governed by 3 principles. They are Aufbau Principle, Hund's rule of maximum multiplicity, and Paulis Exclusion Principle. Thus, the quantum numbers give the complete information about an electron in an atom. There are 4 quantum numbers. They are denoted by n, l, m and s. They are the principal quantum number n, the azimuthal or angular quantum number l, the magnetic quantum number m, and the spin quantum number s. The principal quantum number n describes the size of the orbital and energy of an electron. It describes the distance of the electron from the nucleus. Greater the distance, larger is the size of the orbital. The values of principal quantum number n is given here. N equal to 1 represent the first shell, n equal to 2 represent the second shell, n equal to 3 represent the third shell, n equal to 4 represent the fourth shell, and so on. The azimuthal quantum number L, also called the angular momentum quantum number, describes the shape of the orbital. It also gives information about the subshells present in each shell. The shape of the orbitals are given here. The s orbital is of spherical shape, p has got dumbbell shape, and d is of double dumbbell shape. The azimuthal quantum number has values from 0 to n-1. This means that the first shell has got only one subshell, that is s. The second shell has got 2 subshells, they are 2s and 2p. Similarly, 3 has got 3s, 3p and 3d. The magnetic quantum number m describes the orientation of orbitals in the 3-dimensional space. It also gives information about the number of orbitals present in each subshell. The magnetic quantum number m has values from -l to 0 to +l. Thus the s subshell has got only one orbital with the value 0. P has got 3 subshells with the values -1, 0 and +1. The spin quantum number s describes the spin motion of the electron, whether it is in clockwise or anti-clockwise direction. Now we will discuss the principles governing the filling of electrons in the orbitals. First we will discuss the Aufbau principle. The Aufbau Principle states that the filling of electrons in the atomic orbitals of the elements takes place in the order of increasing energy of the atomic orbital. In other words, the orbitals of the lowest energy will be filled first and then the orbitals of next higher energy. The energy of the atomic orbitals can be derived by using the n plus L rule, where n represents the principal quantum number and L represents the azimuthal quantum number. According to the n plus L rule, higher the value of n plus L, higher will be the value of the atomic orbitals and vice versa. The energy of atomic orbitals follows the following order. This means that the 1s orbital will be filled first, followed by 2s, 2p, 3s, etc. Now we will discuss the n plus L rule in detail. For the 1s orbital, the value of n is 1 and L is 0. So n plus 1 is given by 1 plus 0, that is 1. So it corresponds to the lowest energy. For the 2s orbital, the value of n is 2 and L is 0. So n plus L is 2 plus 0, that is equal to 2. It has got higher energy than the 1s orbital. For the 2p orbital, the value of n is 2 and L is 1. So the value of n plus L is 2 plus 1, that is equal to 3. For the 3s orbital, the value of n is 3 and L is 0. So the n plus 1 value is 3 plus 0, that is equal to 3. Now we can see that both the 2p and 3s orbital has got the n plus L value as 3. In such cases, the rule is that more the value of n, more is the energy. Thus, the atomic orbitals are arranged according to the n plus L rule given by the Aufbau principle. Next, we will discuss the Hunds rule of maximum multiplicity. According to this rule, the electron pairing in p, d and f orbitals cannot occur until each orbital in a given subshell contains one electron each. In simple words, empty orbitals are filled first, pairing occurs later. In the case of oxygen, the electronic configuration is 1s2, 2s2 and 2p4. The 1s and 2s orbitals are filled with 2 electrons each. But in the case of 2p4, electrons should be filled in such a way that each orbital receives 1 electron each and then the pairing occurs. Thus, according to Hund's rule, the 2p orbitals are filled in this manner. In case of 2p4, first 3 electrons will enter in each orbital and then the pairing occurs. Similar is the case of 2p5 orbital. First, 1 electron each enters the 3 orbitals and then the pairing occurs. Identify the correct set of electronic configuration. For nitrogen, the outermost electronic configuration is 2p3. According to Hund's rule, first 1 electron each will enter the orbitals and only then the pairing occurs. So, the first configuration is correct and the second one is incorrect. Next, we will discuss about diamagnetic and paramagnetic elements. Paramagnetic elements are elements with unpaired electrons. They are attracted to a magnetic field. Examples are oxygen, nitrogen, copper, and almost all other elements. On the other hand, diamagnetic elements are elements with paired electrons. They are repelled by a magnetic field. Examples are calcium, argon, zinc, etc. Now we should predict whether the following is paramagnetic or diamagnetic. In case of titanium, the outermost electronic configuration is 4s2 3d2 and there are 2 unpaired electrons in the d orbital, so it is paramagnetic. The outermost electronic configuration of selenium is 4s2 3d10 and 4p4. In the 4p4 orbital, 2 electrons are unpaired, so it is paramagnetic. In the case of strontium, the outermost electronic configuration is 5s2. Both the electrons are paired in the s orbital and thus it is diamagnetic. Next, in the case of cadmium, the outermost electronic configuration is 5s2 4d10 and in the d orbital all the 10 electrons are paired, thus it is diamagnetic. Next, in the case of potassium, the outermost configuration is 4s1, that is only 1 electron in the s orbital and thus it is paramagnetic. Next, in the case of argon, the outermost configuration is 3p6 and all electrons are paired and thus it is diamagnetic. Next, we will discuss about the Paulis Exclusion Principle. Pauli's exclusion principle states that no two electrons in an atom can have same set of 4 quantum numbers. In other words, each electron in an atom has got different set of quantum numbers. For example, let us consider an atom of helium which consists of 2 electrons in the 1s subshell. Now, the values of 4 quantum numbers for each electron is given here. Therefore, both the electrons have the same values for n, l and m quantum numbers, but they have different values for spin quantum number s because the first electron in the subshell has got clockwise spin and the other has got anti-clockwise spin.